Welcome to Vanadium. Sometimes the more I learn about something, the stranger it seems to me. And it shouldn't be true with subjects like chemistry and physics and other branches of the hard sciences. But it is. And what I'm going to talk about today, you won't hear about in your undergraduate classes, your graduate classes. You won't hear scientists speak about it publicly much. There's a few books on the subject, but really, if you want to really get the handle on this, and most scientists probably in the fields will know about this, but you got to get them maybe like by themselves, amongst each other in a place where they feel comfortable, or maybe get them drunk or something like that. And maybe they'll admit to something like what I'm talking about today. But there is something strange, there's something magical, there's something mysterious going on in the world of chemistry, and the world of crystals and crystallography. And a lot of scientists don't like talking about it, because it's kind of hard to understand, and it's easy to write a lot of these effects off if they weren't so persistent and they didn't cross the globe, if the effect wasn't seen by various groups across the world. These things would be easy to write off, but they're a lot easier to ignore than they are to talk about publicly. And a lot of scientists, like everyone else, they just don't want to look foolish. So this brings me to the Mandela Effect. Now, I don't really like the name of this effect, but it's really interesting. So the whole idea was that some people remember Nelson Mandela dying in prison in the 80s. I don't. I remember him dying in 2013. But so the whole idea is that there was a collective misremembering of history, and that some people remember a different history than others. And so is one right, is one wrong? Yeah, that seems to be the way reality works. But this effect, this divergence in memory, is called the Mandela Effect. And what I think it should be called is the Berenstain Effect. Because if you Google Berenstain bears, you're going to see something really interesting on Google. So I read these books as a kid. And I read a lot of them, more than really any other of the series of kids' books. I found them really interesting. And I remember it spelled Berenstain, like Albert Einstein, not Berenstain. This ghastly spelling. First of all, I would have never picked up a book where the title was spelled like that. Second of all, I certainly would have remembered it. I owned these books, and I don't have them anymore, unfortunately. And I don't know where I can find them, but I would remember. It would have formed some sort of memory to have the word stain in the title like that. So history, if you were going to believe it, would just say that I'm misremembering, and I'm just wrong. But to be honest, Vanadium audience, I kind of don't believe it. I think something screwy is going on. So did the world, did history change while I wasn't looking? Yes. So, all right. So we know what happens in literature. But does this kind of thing happen with the physical universe, with physical laws? It's not supposed to. And if you look into it, it's certainly not common. And physical laws seem to transcend time and space. These laws of electricity and magnetism are supposed to be the same across the universe, every spot on the globe. Most of the time, that's true, but not always. And what I'm going to talk about today is sort of like a Mandela effect for crystals, for the physical world. And science, say it isn't so. But there is a Mandela effect that chemists can't ignore. Now, I first heard about this by a guy called Rupert Sheldrake, and I've mentioned him on the podcast before. So his work, he did some work with the Parra Laboratory, the Princeton Engineering Anomalies Research Laboratory that I mentioned in a previous podcast. So he's famous for the idea of morphic resonance. So I'm just going to read from his Wikipedia page. Alfred Rupert Sheldrake is an English author, researcher in the field of parapsychology, who proposed the concept of morphic resonance, a conjecture which lacks mainstream acceptance and has been characterized as pseudoscience. A lot of the good science is classified that way. He worked as a biochemist at Cambridge University from 1967 to 1973, so I guess he wasn't doing all pseudoscience, and a principal plant physiologist at the International Crops Research Institute for the Semi-Arid Tropics in India in 1978. So you'll hear this guy credited with the idea of morphic resonance. There's a structure to living things that goes beyond basic DNA and inherited traits, characteristics. He also he's the guy that first brought me on keeping the idea of random number generators and the work that was going on at Pear. So his base, what's at the core of what Rupert Sheldrake, his idea is the idea that consciousness interacts with complex systems in surprising ways that we would never be able to intuit. So it turns out that our consciousness our collective consciousness especially can affect random number generators, both electronic and mechanical at the Pear Lab. And what's really interesting that Rupert Sheldrake keyed me into is this idea of collective learning and translational learning. So you can teach, let's say you have a group of rats or mice, and they learn a sets of mazes on one side of the world. Now, there's sort of an effect that's been known and documented where rats and mice on the other side of the world will simultaneously get a situational awareness of the maze and be able to solve it in a much quicker time. And that this effect will sort of sweep the globe. And basically the scientists have to go invent a new maze because the rats have stored the solutions to the mazes in their collective unconscious. And even rats that are born without any access to the other rats or access to the maze somehow will learn it faster and just get through the maze. And the maze is no longer an obstacle to them. It's very strange. So this idea of morphic resonance, it's not just with living things, but what about other sort of random number generators and living things? But what about complex systems like crystals? Now, yes, there is something like that happens. So, and I really had a lot of doubts about this. But the idea is that when you first make a substance and you crystallize it, after you synthesize, you put the atoms together in a molecule and you crystallize it, it's harder to make a crystal for the first time. It's a little easier the second time. And as time goes on, crystal chemists, synthesis chemists, can produce the compounds more easily. And this effect is independent of the chemist. So just as time goes on, the more a compound is synthesized, the easier it is to make. And that's something that Rupert Sheldrake, I heard sort of mentioned among chemists, but the whole idea was that somehow seeds of the compounds in the crystals somehow just get around, and they facilitate the growth of the crystals in other laboratories. Even with new equipment across the world without any kind of real obvious chance for contamination, seems sort of, I'm kind of skeptical about that. And a lot of good scientists are, I think, for good reason. But that's how they write off this effect that I'm going to talk about today. So there is a great book by Kurt Vonnegut called Cat's Cradle. And I'm going to read a little passage. There are several ways, Dr. Breed said to me, in which certain liquids crystallize, can freeze, several ways in which their atoms can stack and lock in an orderly, rigid way. That old man with spotted hands invited me to think of several ways in which cannonballs might be stacked on a courthouse lawn, of several ways in which oranges might be packed into a crate. So it is with atoms and crystals, too. And two different crystals of the same substance can have quite different physical properties. He told me about a factory that had been growing big crystals of ethylene diamine tartrate. The crystals were useful in certain manufacturing operations, he said. But one day the factory discovered that the crystals it was growing no longer had the properties desired. The atoms had begun to stack and lock, to freeze in a different fashion. The liquid that was crystallizing hadn't changed, but the crystals that were forming were, as far as industrial applications went, pure junk. How had this come to be was a mystery. The theoretical villain, however, was what Dr. Breed called a seed. He meant by that a tiny grain of the undesired crystal pattern. The seed, which had come from God only knows, taught the atoms the novel way which to stack, to lock, to crystallize, and freeze. Now, it turns out that Kurt Vonnegut wasn't making that up. He was referencing a real story, and he actually had a background in chemistry. And the paranormal chemical entity in question is ethylene diamine tartrate. And it was first synthesized at a large scale. It was synthesized before that in the laboratories in the 20s. It was first synthesized on a large scale in big industrial vats across the world in the 40s, and in anhydrous form. And what anhydrous means is that the chemical just contains ethylene diamine and tartrate locked into a sort of a salt form with no water in the crystal. And that went on for 2 decades. And the material was a useful piezoelectric material that was gaining a lot of applications for force sensors and things like that. So ferroelectrics, piezoelectrics are the same thing. Then, in 1960, something strange started to happen. A hydrate crystal with undesirable properties, or a lack of the piezoelectric property, started to appear in the production processes across the world. And chemists tried to stem the tide of these hydrate crystals, but pretty soon they couldn't even make the anhydrous variety. And chemists in 1965 had to give up production entirely. A crystal is a system satisfied. The atoms slow down from the gas and they begin to come together and condense into a liquid, and eventually they come together into a solid. And then ultimately they arrange in the most comfortable way possible, where every atom in the system is the most satisfied. And that's a crystal. That's a thermodynamic equilibrium. So another example from Rupert Sheldrake is something called Xylitol. So in 1891, this was first synthesized at a large scale, and it's an artificial sweetener. And actually, it was really useful. It was a liquid that you just put into coffee and other beverages, and it was gaining quite a fanfare. It was made at the ton scale in the liquid form, in pure variety at room temperature. And then, about 50 years later, solids started forming in some of the vats. And no one knew why, but all of a sudden, this former liquid at room temperature was now a solid, and at a melting point of 61 degrees Celsius. And so people at the time didn't know what to make of it, and they couldn't really figure out what was going on, but they said, okay, xylitol is now a solid with a melting point of 61 degrees Celsius. And everybody was happy with that for a while, until 1969, when a new crystal phase formed that had a new melting point, had similar properties, but it was a higher melting point, crystal solid, and that they could no longer get the liquid or the lower melting variety at room temperature. And all they could produce was this new crystalline solid with a melting point of 94 degrees Celsius. It's been the same since from 1969 till today. Now, what is going on here? Now, there's a great paper in the Journal of Applied Crystallography in 1975, and it's called Unusual Crystallization Behavior. Now, scientists don't like to use the word unusual, but I'll read you the beginning here. There are many instances, some reported in the literature and others not, of crystalline compounds behaving respectably for many months or years, until nucleation of a more stable form. After this occurs, the previously obtained crystal cannot be made to crystallize even in laboratories many miles away. We've recently encountered such an event and became interested in the prevalence of such behavior. The results were so interesting to us that we felt your readers might be equally interested. This article, they go into something that's a really strange story of a drug called Ampicillin, which is related to penicillin. Now, the original patent was invented in academia, but the original patent holders of this was a company called Beecham. And they held the patents on a form of ampicillin monohydrate. And for years, they were selling this and making a lot of money, until Bristol Myers wanted a piece of the action. And Bristol Myers said, you know what? We have a new form that we've created in the lab. It's not ampicillin monohydrate, it's ampicillin trihydrate. It's new, everybody. And so Beecham and the patent attorneys were like, hold up. A, that's really not all that novel, just having a different hydrated form. But you know what? We were wrong. That monohydrate never really existed. It was always a trihydrate. So they were aware that they were no longer forming the monohydrate, and that the company Beecham, they had lost the ability to make the monohydrate, and they were making this new form all along, and it had the same properties. But Bristol Myers came along, and they thought that they were just going to come in and they had invented something new. And they even tried to recreate the original monohydrate form using the patent literature from Beecham, and they couldn't do it. The only form they could get was this trihydrate. It was as though the monohydrate never existed. So that's a strange story of ampicillin. There's another article in the Academies of Chemical Research. And this is talking about some sugar molecules. Molybios and mannose. The Feinstahl Chemical Company in Waukegan, Illinois, specialized in isolating and purifying natural products. One of these was the disaccharide beta-molybios, with crystallization as the final purification step. The production ran into a problem. Then one day, for no apparent reason, the molybios turned out to be of the alpha variety. Try as they might, the Feinstahl chemists could not get a batch of molybios to crystallize in the beta form. They finally concluded that mere traces of the alpha form in the air or on the equipment were enough to seed the solutions. But where it came from was never determined. They gave up manufacture of that particular item, but are convinced that in some other locality in which there is not a trace of the alpha molybios, it could be possible to crystallize the other form of the sugar. Now they just gave up. So it's as though some crystals just take over. They learn from each other, and the other forms just die out. They've evolved, and the other forms are just deceased, dead forever. Are these crystals talking to each other? So Rupert Sheldrake has a book called Morphological Resonance, and he goes into some of the stuff I've discussed and also some other stuff on crystals and new chemical compounds. So he cites some examples here of natural compounds and basically synthetic modifications where they take, for instance, salicin is basically like aspirin. It's a natural form of aspirin before they add an acetyl group to it. So these natural compounds, cocaine's another one. And these compounds have been known for basically since the early days of chemistry. And the compounds of the natural compound, the melting points of the natural compounds have stayed pretty constant. But what people have observed is that these synthetic compounds that have been made, the melting points are slowly going up. Not only are they forming new crystal phases, and the older phases are becoming difficult to synthesize and disappearing, but its accepted crystal phases are developing higher melting points over time, and no one can account for this. This makes really no sense. And it's something that is difficult to write papers about because it just looks like you're doing all of your experiments wrong. And there's some great examples of this. So one other one is, this is related to cocaine, benzocaine picrate. It's a low-melting 132-degree form, has been used as a standard in pharmaceuticals until a higher melting form came around, and you can't get the lower melting form anymore. And this, I have a couple. I'll give some examples, some other articles that show some other compounds that show the same effect. And here's a quote from the article. Within the fraternity of crystallographers, anecdotes abound about crystalline compounds which, like legendary beasts, are observed once and then never seen again. I mean, could this really be for real? It seems like it is. And it's getting written about more and more. And not only is it in the scientific literature, but actually it's found its way into some video games as well. So there's a game that I'd never heard of called 9 Hours, 9 Persons, 9 Doors. And in this game, apparently, they talk about glycerin, or glycerol is another name for it, and crystallization of glycerol. And in the game, they talk about how one day, glycerin, which for many years, the crystalline form had never been reported in literature, just started crystallizing. Just one vat of it somewhere. And then it became fairly easy to crystallize around the world with no explanation. And this is also referenced by Kurt Vonnegut in Cat's Cradle as well. But it turns out that this story, there is some truth to it. And this is a little easier to explain away with experimental techniques because it is a little bit difficult to crystallize glycerin. I'm actually working on that in one of my own experiments. So glycerin is an important chemical. It's used as a lubricant, food additive, and different industrial ingredients. But for a long time, people thought you really just couldn't crystallize it. And people believed the crystalline form just did not exist. That's a bunch of nonsense. Until a mysterious barrel full on a British cargo ship completely crystallized one day. And then after that, people could they could readily prepare glycerol. And so this, I looked into this a little bit, and some people tried to explain this away as a myth. But it turned out there is an article that referenced this, and there's some truth. And I have the reference here from the Journal of the American Chemical Society from 1923. So there was definitely something to this. Benzophenone is another example. So for years, it was at room temperature thought to be a liquid until it sort of mysteriously just started forming crystals, and then became now known as a solid at room temperature. So you cannot keep some crystals down. Now, these are some examples of in the sciences where things shouldn't be mysterious, yet they are. And that's what makes it so wonderful. So with times being so tough out there in the world, just keep that in mind, that the world is a wonderful and mysterious place. And don't let all the negativity get you down. Or at least not let it get you down so much. This is Christopher Rankin, and this is Vanadium. Thank you very much.